this point as x equal to a. So let the energy of the particle be E, which is greater than V. Okay, so energy of the particle is E, which is greater than V. Now what happens is, so let us note this region as region 1, and this region as region 2, and this region as region 3. So we can write down, now that we have done this kind of problems earlier, so we can directly write down the solution of the Schrodinger equation of the wave function in different regions. So psi 1 of x is equal to, so let me call this as let's say some a1 into e to the power ikx plus a2 into e to the power minus ikx. Okay, so what is k here? K square is equal to twice m e by h bar square. Okay, so that is the wave function in region 1. Now the wave function in region 2 of x is equal to, so let us have b1 into e to the power I alpha x plus b2 into e to the power minus I alpha x, where alpha square is equal to twice m into e minus v naught divided by h bar. This is positive because e is greater than, since we are working with problem in which e is greater than v naught. And then we can write down the third region, psi 3 of x, to be c e to the power ikx, because their energy is 0, so I have c into e to the ikx. There is no reflection, so e to the minus ikx term will not be there. So these are the wave functions in the 3 different regions. Now we have to use boundary conditions. Boundary conditions at 2 different potential variations. One is at x equal to 0. So that there are totally 4 boundary conditions. Psi 1 at x equal to 0 is same as psi 2 at x equal to 0. This is the continuity of the wave function. And now the potential is finite, and therefore the derivative of the wave function psi 1 prime at x equal to 0 is also same as psi 2 prime at x is equal to 0. This is as far as the boundary x equal to 0 is concerned. Now when you go to x equal to a, you have psi 2 at x equal to a is equal to psi 3 at x equal to a. And psi 2 prime at x equal to a is equal to psi 3 prime at x equal to a. So these are 4 boundary conditions that I have. Now you can see that this boundary condition implies I have A1 plus A2 is equal to B1 plus B. Okay. Then this boundary condition implies Ik times A1 minus A2 is equal to I alpha into B1 minus B. Now this boundary condition implies B1 e to the power I k b to the power I alpha A plus B2 e to the minus I alpha A is equal to C e to the power I k. Okay. Then this boundary condition implies I k times B1 e to the power I k A minus B2 e to the minus I k. This is alpha A. Alpha A is equal to I k C e to the power I k. Okay. So now you can see that I can take this to this side so that I cancels and I have alpha by k. I alpha. I alpha. Now these two equations I can write down. Suppose if I add these two equations, I will have A1 is equal to half. I'm going to add. Okay, that means B1 into 1 plus alpha by k plus this half is common plus B2 into 1 minus alpha by k. Okay, so this is my A1 and A2 I will get by subtracting that one. So A2 will be equal to half B1 into 1 minus alpha by k plus B2 into 1 plus alpha by k. Okay, so I have got A1, A2 in terms of B1 and B2. Now I will, so let's say that, so let us say that I am interested in, let us calculate transmission coefficient. Transmission coefficient. Which is defined by C divided by A1 modulus square. C divided by A1 modulus square. So I have this expression for A1 here. Now if I get B1 and B2 in terms of C from the last two conditions, I will be able to get an expression for the transmission coefficient. So now what I will do is, here also let me take this on the other side. So it will become k by alpha. So if I add these two things, okay, so if I add these two things, I can write down B1, okay, Okay, it is actually 2 times b1 into e to the power I alpha a is equal to 1 plus k by alpha into c into e to the power I k. Correct? Or in other words, I can write down this b1 to be half into 1 plus k by alpha into e to the power minus I alpha a into e to the power I k a into c. Please note that this kind of bookkeeping is very important in doing calculations in quantum mechanics. Now I will subtract this equation. That will give me 2 times b2 into e to the minus I alpha a is equal to 1 minus k by alpha into c into e to the power I k. So that gives me my b2, which is equal to half into 1 minus k by alpha into e to the minus e to the plus I alpha a into e to the I k a into c. So I have an equation. Okay, so let us call this as equation. Let's call this as equation 1, and this as equation 2, and this as equation 3, and this as equation 4. Okay. Now substitute 3 and 4 in 1, equation 1. Okay. So that I will get, now A1 is equal to, there is a 1 by 2 here and there is a 1 by 2 here, so it will be 1 by 4. Okay, so 1 by 4 into, so here I have B1 and here I have B2. I'm going to substitute for B1 and B2 in terms of this. So this is equal to 1 plus alpha by k into 1 plus k by alpha, 1 plus alpha by k into 1 plus k by alpha into e to the minus I alpha a into e to the power I k a. Okay, c is there in both the terms, so let me just write that c already on the left hand side like this. Plus, I have 1 minus alpha by k, 1 minus k by alpha, e to the power I alpha a into e to the I k. Okay, so that is, so all that we want is c by a1 square. I have got a1 by c here. So I have to simplify this expression and then take modulus square of that. So you can see that this is nothing but, so this is k plus alpha by k, alpha plus k by k. So I can write this as 1 over 4. This e power I k a is a term which is sitting here and which is sitting here. So I can write it as e power I k a divided by alpha k into k plus alpha the whole square into e to the minus I alpha a plus, so you can see this is k minus alpha, this is alpha minus k, so I will have to pull out a minus sign and write this as k minus alpha whole square into e to the I k. That this is alpha. Okay, so please check this. I am alpha and k. I think I am getting little confused. So I am writing. So whatever is k is taken outside. So whatever is inside is alpha. So this is equal to e to the power I k a divided by 4 alpha k into. So if you expand this, okay, so I have k square plus alpha square plus 2 alpha 2k alpha into e to the power minus I alpha a minus you have k square plus alpha square minus 2k alpha into e to the power I alpha a. Okay. Now you can see that if you take this 2k alpha and minus into minus 2k alpha is plus 2k alpha. Okay, so that will give you e to the I alpha a plus e to the minus I alpha a. So that is e to the I k a by 4 alpha k into 2k alpha into e to the I alpha a plus e to the minus I alpha a. Okay. On the other hand, I have minus k square plus alpha square. Pull out a minus sign. Then I will have e to the I alpha a minus e to the minus I alpha. Okay. So now you can write this in terms of cos and sine. So this is equal to, so this is essentially 2 cos alpha a, and this is 2i sine alpha. 2 cos alpha a, 2i sine. So then I have this e to the I k a divided by 4 alpha k to 4k alpha into cos alpha a minus 2k square plus alpha square into I into sine alpha. So what is this? This is my a1 by c. Suppose if I ask, so let me ask what is 1 by t. 1 by t is a1 by c mod square. Correct. So that is equal to, this is e to the I k a. When you multiply this one with its conjugate, it will become 1. So this is just a complex number with unit modulus. So this will not, that will become 1 when you take mod square of that, right? So you have, so you have something. So let's take this 2 out. So let's say there is a 2 here, and then that 2 can 2 there. So when I square, what I will have is 4k square alpha square cos square alpha a plus k square plus alpha square the whole square into sine square alpha a divided by 4k square alpha square. So this is the expression for 1 over 2. Now I can write this, simplify this further by writing this as 4k square alpha square into 1 minus sine square alpha a plus k square plus alpha square whole square into sine square alpha a divided by 4k square alpha. Now you can see that this is k square plus alpha square minus 4k square alpha square is k square minus alpha square whole square. Okay. So I can now write down the reciprocal of this. The transmission coefficient is equal to 4k square alpha square divided by 4k square alpha square plus k square minus alpha square whole square into sine square alpha. So this is the expression for the transmission coefficient. Okay, but note that my k square is twice m e by h bar square, and alpha square is twice m e minus v naught divided by h bar. Correct? So that means I can now write it in terms of this. So this transmission coefficient, what will be k square minus alpha square? K square minus alpha square is equal to this twice m e by h bar square will cancel. So you have twice m v naught divided by h bar square. Okay, twice m v naught divided by h bar square. So you can see that this factor twice m by h bar square will be there in all. So there is one twice m by h bar square here, twice m by h bar square here. So it will be square of that, and in every term that square is there, so that will cancel away. So you will have 4 e into e minus v naught divided by 4 e into e minus v naught plus v naught square into sine square alpha. Okay, so I can write this in the following fashion: E is equal to 1 divided by 1 plus v naught square divided by 4e into e minus v naught into sine square alpha. Okay, so this is essentially the transmission coefficient. So what is transmission coefficient? It is the probability. This is essentially probability of transmission. Probability of transmission. Now notice two things here. If you are looking at sine square of any quantity will vary between 0 and 1. Okay. So suppose if sine square alpha a is equal to 1, then the transmission probability is minimum. Okay, because this denominator is maximum and transmission coefficient is minimum. But if sine square alpha a is 0, then the transmission coefficient is 1. Okay, so you can see that t varies between you have this 1 by 1 plus V0 square divided by 4E into E minus V naught and 1. Okay. So if you, that is, if you are actually trying to vary this Ka, let's say that we are going to plot let's say alpha into A on the x-axis and T on the y-axis. So when alpha A is equal to 0, it is 1, and then it will come down to some minimum and then go to 1 again, come down to a minimum, okay, go to 1 again, like this. Okay, and this minimum where it comes down, okay, so everywhere it comes down to minimum. So the minimum that it comes down is this value. This value is this minimum, and this is 1. Maximum is 1. And when does this maximum happens? So t is equal to 1 if alpha times A is equal to n times pi. Alpha times A is equal to n times pi. Because sine 0, sine pi, sine 2 pi, all those things are 0, so this becomes 1. Now, what is the meaning of saying t is equal to 1? T is equal to 1 means this is sure transmission. Sure transmission. Okay. Now you can ask a question that this is what is called resonant transmission. Okay, resonant transmission. Now you see, in general, okay, so you can notice here that in general, this quantity is greater than 0 because E is greater than V naught. This is square, and sine square is a positive number. This is a greater than 0, and hence your T is less than 1. But it is equal to 1 if this condition is satisfied. Okay, such a transmission is called. That means it is for sure is getting transmitted. That means the particle comes out. There is a reflection in general. That is why T is less than 1. In there is a reflection at two boundaries, but even in the presence of that, whenever this condition is satisfied, then there is a transmission with unit probability. Now we can ask a question: what is this condition, or what does this condition mean? For example, let's say that you write alpha square A square is equal to n square pi square. Now alpha square we know is twice m by h bar square into E minus V0 into A square is equal to n square pi square. Or in other words, I can write this. Okay, so let me write this one as E minus V naught. E minus V naught is equal to n square pi square into h bar square by twice m A square. Okay, or in other words, you can say that it's E is equal to V0 plus n square pi square h bar square by twice m a square. Now, this energy that I have written here should be probably ringing some bell in your mind. What are these energies? Now, if you look at this picture, I have a barrier like this. Okay. Now, let's say I have some energy here. Let's say this is my energy. Okay. And if this is my V naught, whenever the energy is equal to V naught plus or whatever E minus V naught, okay, whenever this E minus V naught is equal to the energy levels of some kind of a infinite square well. Suppose if you imagine that you have got some infinite square well here, okay, that means it's like particle in a box, both sides infinity. What are the energy levels of particle in a box? Exactly, these are the energy levels, right? If n is equal to 1, it is a ground state. If n is equal to 2, it is a first excited state. So these are, so note that this n square pi square h bar square by twice m a square are energy levels of an infinite well of size a, okay, of size a. So from the top of this barrier, if your energy is equal to one of these particle in a box energy levels, then there is a sure transmission. So why does this happen? What is the connection? Okay, why do you think there is a connection between these two? Okay, so this is one interesting observation that we can make here. Okay? So I want you to think a little bit on why. Why is this connection? Now, you can do two things from here. For example, suppose if you have a so there is some more problems. Without solving them, we can get results. That is, for example, let's say that you have a square well like this. Okay, so let's say this is 0 and this is minus V naught, and we are trying to ask energy of the particle is greater than 0. That means about. Now you can ask what is the transmission coefficient. Okay, so whatever we have done is valid. Everything is valid, except that now you are going to replace replace E minus V naught by E plus V naught. That's all. Okay, replace in the previous expression, wherever you have E minus V naught, replace by E plus V naught. This is scattering problem for getting transmission coefficient. This is one problem, the scattering from square well potential. Now we can also ask another problem, that is we have square barrier, that is we have a barrier. Okay, so I have V naught, but now let's say that the energy is less than V naught. Okay, so what is this problem? This problem is called tunneling. That is, even if energy is less than V naught, classically there is no transmission possible, but quantum mechanically transmission is possible. So you get a tunneling. Now, how do you do? The mathematics is exactly same. Okay, so in fact, I am not going to do mathematics. So if you want to find out the tunneling probability, I'm going to get the tunneling probability. So let's say you replace alpha by some I times, if you want to call, you can say I times beta. Why? Because E is less than V naught, this alpha is now an imaginary number, I times beta. Now if you do this, so you can go back and look at this transmission coefficient. Okay, so you can see this becomes alpha 4k square alpha square, okay, or maybe I should put so you can see that this transmission or the tunneling probability is equal to 4k square beta square divided by 4k square beta square plus k square plus beta square into sine hyperbolic of beta into A. Sine hyperbolic square of beta into A. So this will be your tunneling probability. Because I have now set alpha is equal to beta A, I will get this expression. So you can see that we have solved many problems with this one problem, because the methodology that we have used, namely the boundary conditions, etc., are going to be same for all these problems, and hence you don't have to redo the problem. Okay, so this is and let me also tell you that this particular resonant transmission is a useful tool. For example, let's say that so if I know, okay, so using this resonant transmission, we can find A, that is the barrier width by varying energy. Okay, so that means like you have, let's say, there is some kind of a system here. Let's say there is a particle, and this particle may have some range of interaction. Okay, so if you want to model, you must model this range of interaction to be something like this, like a barrier. So this is your A. Now you go on sending particles with so this is like a scattering center. Now you go on sending particles with different energies. Now you see at some particular energy there will be resonant transmission. Okay, so of course you should know V. Okay, so you should know V. You should know V naught. If you know V naught, then by varying energy, we will be able to determine A. Or if you know A, then you can find out the strength of the interaction. Okay, so this is usually the scattering experiments that people do. Like when people were trying to understand what is the size of the nucleus, etc., they try to do the scattering experiments. So they send electrons of different energies, and then they see when this kind of a resonant transmission occurs. So that will fix some kind of a barrier height if you know barrier width, and barrier width if you know barrier. So you have to do two different experiments. So from one experiment, if you can find out A, and like for example, in trying to find the size of the nucleus, they actually sent electrons, and when the electron is going through, so let's say you have a nucleus here. So let's say you have a nucleus here with this much of charge, and then yeah, just a minute. Then you have an electron, and electron is sent, and then it scatters. So you know that the scattering is basically follows Rutherford scattering, and we know Rutherford scattering cross section, and we see whether our experiment is agreeing with this Rutherford scattering cross section. Now what happens if you are increasing the energy of this electron higher and higher, it will go closer and closer to the nucleus. Now they carefully looked at the experimental scattering, and when does it deviate from the Rutherford scattering. So that means if it is deviating from the Rutherford scattering, that means this electron is seeing some other interaction which is different from the Coulomb interaction. So they looked at so at some particular energy, when the energy is more than some particular value, the electron scattering will not obey Rutherford scattering any longer, and then they can calculate with that energy, and they can calculate what is the size of the nucleus. So once you find the size, then you can do this resonant transmission kind of experiment to find out what is the strength of the interaction. Yes, Shitik.
You answered actually, sir. I was asking how in scattering problem we will replace this 1D problem, one dimensional.
Yeah.
Yes, sir. Thank you. So, sir, this deviation only tells there the presence of some non-central potential, or
It's not necessarily non-central. See, Rutherford scattering is just Coulomb potential, right? Even if
yes,
it is
sir.
central potential, if it is a non-Coulomb type potential, then the cross section will be different. So we we will not know whether it is non-central or not by just this deviation, but this deviation tells you that there is something more than the Coulomb interaction that is present.
Yes, sir. Yes, sir.
So this is kind of a very nice problem where you can you can calculate these things quite easily, except by some simple bookkeeping. At the same time, you can get the condition for the resonance. Now let's go back to this question that we asked. What is the connection? Anybody has some clue? Why is there a connection to this particle in a box energy levels? Have you noticed this anytime?
Sir, is it because since there is a drop in the potential, there is also a reflection happening?
Yes, reflection happens.
So is that why? So it essentially becomes like a particle in a box problem.
Reflection happens, but why should it be totally reflected? You see, if it is particle in a box, infinite potential, then it gets totally reflected. No, there's nothing that comes this side or this side. There's no wave function on region 1 and region 3 in the particle in a box, right?
Yes, sir, that's correct.
Sir, in like the energy in square pi square h bar square by 2m square, the corresponding wave functions there, maybe sine or sine, those have the nodes at the boundary. So they can continue from there in that condition in both sides. Here we have some wave function on the left side also, on the right side also. So we have this particular energy, this V naught plus this quantity. So the corresponding wave function there may be such that the nodes can continue from there. From the nodes, it will continue wave function. So
Okay.
it can transmit properly, like with no reflection, only transmission only.
Okay. So I think you seem to have some. You seem to be in the right direction of the answer. But to understand why this happens, let's try to examine this. So t is equal to 1 happens when your sine alpha a is equal to 0, correct? That means your alpha a is equal to n times pi. Okay. So let us say that let lambda be the wavelength in region 2. Okay, that is in the barrier region. So that means we can write down this alpha to be 2 pi by lambda, correct? So we have 2 pi by lambda into A is equal to n pi. Or in other words, let's cancel this pi. In other words, we say that this A is equal to n times lambda by 2. Okay, A is equal to n times lambda by 2. So now if you look at this barrier region, so let's say n is equal to 1, that means this for the energy for which n is equal to 1, this wave function looks, this wave looks like this, correct? This is half the wavelength is equal to A. Or if you take that it is 2 half wavelengths, that means it will be It will be like this. Full wavelength. Okay. Now, if you see these shapes are exactly the wave functions of your particle in a one-dimensional box. In other words, this condition tells you that in this region there will be some kind of a stationary waves. Okay, there will be some kind of a stationary waves. Okay, so whenever this kind of a stationary waves are formed, then there is it is like you are already starting from zero at this point. Okay, so that means you have kind of a transmission completely. This is what resonance happens, and whenever so this is related to stationary states. So once you have the stationary states, now with respect to the wave function in this region, the boundary conditions that it will satisfy will be same as the boundary conditions that particle in a one-dimensional box satisfies. Okay, mathematically speaking, once the boundary conditions are same, then the energy levels are fixed, because their energy levels are determined by the boundary conditions. And that is the reason why you will see whenever energy above this V naught is equal to this particle in a box energy levels, you have a resonant transmission. Okay. Suppose if you have this kind of a situation, let's say this kind of a situation, then your situation will be that your E plus V naught is equal to n square pi square h bar square by twice m a square. That means your that's what I said, wherever E minus V naught is there, you put E plus V naught. That means from the bottom of this potential well, you have to see what is the energies of the infinite square well. Okay. So that is the condition for the resonant scattering. Okay, so I think this is one class of problems that we have.
Sir,
yeah.
sir, then in the both in the like region 1 and region 2, whatever the wave function is there, it should continue in the same way.
It should continue
In the same nature, like you have drawn sine wave in the region 2. So region 1 and 3, these wave functions should continue in the similar manner, like in the similar shape.
Yeah, it will be it will continue. For example, it is becoming 0 here, and then it will start from 0. Okay,
Yes,
so it will start from 0 and then it will continue like this. So that continuation will be there. So
Sir,
now I think, is there any question? Yeah.
sir,
Yeah.
that finite square well, can you little discuss about the bound state of that problem?
Yeah, I haven't talked about bound state. This is only about scattering states, that is
Yes,
free
sir.
states. Okay, so we will discuss about the bound states.
Okay, thank you.
Okay, so now let me look at another problem. This is so I don't know what kind of.
Sir, one small doubt, sir.
Yeah.
Sir, the wave function that we plot in the diagrams, those are complex valued functions, no, sir?
But we have seen that wave function, right? So you have a plus. You can always have both. I mean, you mean on the right hand side, is it? On the region 3.
Yes, sir. We can't plot complex valued functions.
Yeah. So, but what I'm saying is that this is basically when you have psi of x. Okay. So you can always plot real part of psi of x or imaginary part of psi of x. Each one has some information, correct? So you can plot real part or imaginary part.
Okay. That's what.
So that can be plotted, right?
Those are real values only.
They are real values.
Okay.
So let's look at the second problem. This is slightly interesting problem, but I will not look at square rule immediately. But let me consider a problem like this. This is you have an infinite barrier here. That means it goes up to infinity. But then this is 0, and this has only some kind of a finite height here. So this is V naught. Okay, let's say this is 0 and this is A. Okay, so if you want to write down, you have a one-dimensional potential which is equal to infinity if x is less than 0, less than or equal to 0, and 0 between 0 and A, and V naught if x is greater than or equal to. Now this potential is interesting because, as I told you earlier, with respect to a one-dimensional delta function, this potential is also like a kind of a cartoon kind of a potential, or a one-dimensional mimic. What happens is generally any two-body interaction potential, a two-body interaction potential okay, with respect to as a function of separation between them typically will be like this. So there may be different potentials. Suppose let's say this is your V of R. R is the separation between them, and this is R. Now typically you will have potentials of this type. Hydrogen atom also you have a potential like this. So what happens if you have one particle here and another particle here? When they are far away, there is an attractive force. When they come very close, there will be some repulsive force. Now this is very generic between for any interaction potential. For example, if you take two molecules, let's say there is some kind of Lennard-Jones kind of potential. There can be different names for the potentials, but the generic feature of the potential is something like this. That means there is some kind of a minimum value of the potential here, which you call it as R naught, and that will be the equilibrium distance between them, or that is where actually there is a bond that forms, and these two atoms will become a molecule or something like that. So there is a generic nature of the interaction potential. So this potential is some kind of a mimicry of this potential. So I'm going to say that this potential addresses the issues of a general interaction potential of any in between any two systems, any two particles. So that is why this is very important, because whatever we understand from this potential, these results are in general will have some relevance to any interaction potential between any two pair of particles. Okay, so that is why this problem is of very importance in physics. So let's look at bound states. Okay, so let's consider look at bound states. Okay, for the particle to be bound between 0 and A. Okay, so E less than V naught. Okay, is necessary. Is necessary for a particle to be bound in 0, comma A. Okay, but we will realize, but it is necessary, but it is not sufficient. It is not sufficient. Okay, we will see why it is not sufficient. It is necessary, but it is not sufficient. So let us go ahead and try to solve the problem. So let me call this one as region 1, and this as region 2, and this as region 3. And we started with this condition that E is less than V naught. So let me write down the first region. Since in this region 1 there is infinite potential, so I don't have any probability that the particle is there. So psi 1 of x is equal to 0. Now psi 2 of x, since E is less than 0, I have A cos kx plus B sin kx. Okay. Now you could have written a e power ikx, b e power minus ikx. These are equivalent, writing in terms of cos kx and sin kx. But whenever we talk about bound states, it is mathematically convenient to write it as cos kx and sin kx. Whenever we are using scattering states, it's mathematically convenient to write it in terms of e power ikx and e power minus ikx. And third region, of course, here k square is equal to twice me by h bar square. Now, third thing, since E is less than V naught, there is going to be an exponential solution, and there is no e to the power. So you can define something called alpha square is equal to twice m V naught minus E divided by h bar square, and you can write down this to be c into e to the power minus alpha x. I don't have plus alpha x. If I have plus alpha x, then as x goes to infinity, this wave function will go to infinity. So that is not there. So these are the wave functions of the three regions. Now the boundary conditions. Okay, so the business is same. So boundary conditions. So psi 2 at x equal to 0 is 0. That implies I must make A to be equal to 0. Because if A is not equal to 0, then psi 2 at x equal to 0 is not 0. So A is equal to 0. Then I have psi 2 at x equal to A is same as psi 3 at x equal to A. Psi 2 at x equal to A is same as psi 3 at x equal to A. This implies, now I have A to be 0 anyway. So B sine Ka is equal to C into e to the minus alpha A. Now the potential there is finite, so its derivative also should be continuous. So psi 3 prime at x equals. Now this implies I have P k cos Ka is equal to minus alpha C e to the minus alpha. Okay. So these are the two different conditions. So now I can write from these two equations. So I take this and divide this by the first equation. So I have K cot Ka is equal to minus alpha. K cot Ka is equal to minus alpha. Now recognize that this condition, this is a condition that gives us allowed values of A. Therefore, energy. Therefore, energy. That means this is what gives rise to energy levels. This is what gives you energy levels. Okay. So just to tell you, in particle so in the case of particle in a box, okay, we had a condition like this: Ka is equal to n pi. Okay, so this condition is equivalent of this condition, because this is what gave rise to allowed values of K and allowed values of energy in particle in a box. Now in the particle in a half box, okay, one side is still infinity, but one side is not infinity, is given by this. But you can see that it is not very easy to get the allowed values of energy in this case, whereas K equal to n pi is straightforward. So let us multiply A on both sides. Okay, so we multiply A on both sides. Then we have K times A into cot Ka is equal to minus alpha. And then now you define some xi is equal to Ka and some eta is equal to alpha. So I have psi cot psi is equal to minus. Now I have to solve this function. Okay. So we need to solve this. This equation is called transcendental equation. Transcendental equation. Why is it called transcendental equation? Because you have, what is eta? Eta is basically, suppose if you ask what is eta square is alpha square A square. That is equal to, what is alpha square? Alpha square is twice m by h bar square into V naught minus E. Okay, so V naught minus E into A square. So this is twice sum E by H bar square is your K square, right? Or Xi square. So this is nothing but twice M V naught A square by H bar square minus Xi square. Okay. Or in other words, your eta is equal to square root of twice M V naught A square by H bar square minus Xi square. So right hand side is also a function of the left hand side, that is LHS is a function of Xi, and right hand side is also a function of RHS is also a function of Xi. Whenever both sides are functions of Xi, we call such equations as transcendental equation. But notice that this is this can be written as
Sir,
yes.
so I thought that transcendental equations means that they are not algebraic. Means they cannot be solved to an algebraic equation, like a polynomial.
Correct, correct.
But here, what is the connection between these two things? Sir?
See, you can have a non-algebraic equation, but yet you can probably solve them without if your right hand side and left hand side are not having the same function of Xi, for example.
Okay, sir. Thank you.
So now you can see that if I take this Xi square on this side, okay, so note that Xi square plus eta square is equal to twice M V naught A square divided by H bar square. So if I take a square root of this one and then make it a square, that means in eta z eta xi plane, in eta xi plane, the above equation is a circle. Is a circle of radius. The radius is given by square root of twice M V naught A square divided by H bar square. Okay, this is the equation of a circle. This is an equation of a circle in eta xi plane. X square plus y square is equal to something. Xi square plus eta square is equal to something. So we have to solve this problem. Okay, so we have to solve this. Solve this equation. There are two ways to solve it. One is a graphical method, graphically, or you have to solve it by using a computation. Okay, computationally using something like Newton-Raphson method. Okay. So these are the two methods in which one can solve this equation. But let me try to solve it graphically, or try to at least present how to solve it. So you know that let me just plot. So essentially the graphical method is the following. So graphical method is LHS and RHS are functions of xi. So plot LHS and RHS separately. Okay. Now points of intersection of the two graphs are the solution. Okay, they are the solutions. So plotting this one is, suppose if I have, let's say I have, so let us say I have two functions. My LHS is minus xi cot xi, and my RHS is simply eta. Okay, but notice that eta versus xi is a circle, so we don't have to do much in that. Eta versus xi is a circle, so we have to plot this LHS. Now let's say that you have 0 here and pi by 2 here. Let's say pi by 2 and pi, 3 pi by 2 and 2 pi. Okay, let's say it is like this. What is cot 0? Cot 0 is, first let us plot cot psi or minus cot psi. Okay, so minus cot psi. So cot 0 is cos 0 by sin 0, that is infinity. But minus cot psi will be minus infinity. And at pi by 2 it should become 0. So you see that this graph will become 0 here, and at pi it goes to plus infinity. So this is your pi minus, it will exactly go to plus infinity like this. Okay, and then it repeats at 3 by 2, again it will be 0, and it repeats like that. But let me not draw the other things. Now, what is xi? Xi is simply, let's, in the same graph, let me draw xi. Xi is simply a straight line. This is your xi. So if I multiply this and this, what happens? This curve, the nature of this curve does not change much. Okay, it will a little bit get extended. So if I draw this picture for, let's say this is pi by 2, and this is pi, and this is 3 pi by 2, this is 2 pi. So you can see that it is going to minus infinity, 0, and then it will go to infinity. So it will again go like this. Like this. It goes on and on and on in this. This is what I have drawn is minus xi cot xi. Now suppose if I want to draw eta versus xi is a circle. That's what I have written here. Eta versus xi is a circle. That means depending on the value of the radius, I can have a circle like, I can have a circle like this. Suppose I have a circle like this. Okay, this is for some particular value of V naught. Okay, there is no solution. That means there is no xi. Okay, whatever I have here is xi. There is no xi such that right hand side and left hand side are intersecting. Correct? So that means the radius should be sufficiently large so that there is an intersection. Now you can see that the intersection will have first intersection will happen when the radius is equal to pi by 2. If anything less than pi by 2, there is no intersection. So if you want to have an intersection between the circle and this curve, it should be pi by 2. That means you have for small v naught, the circle in eta xi plane does not intersect minus xi cos psi. What does that mean? That implies there exists no bound state. There exists no bound state. There exists no energy for which a particle is bound in the region 0 to 8. Now, the minimum value of E naught. Okay, so minimum value of V naught for the existence of a bound state is given by the condition that the radius of the circle in eta xi plane, namely square root of twice m V naught a square divided by h bar square, should be equal to pi by 2. That means your V naught should be equal to square on both sides, should be equal to h bar square pi square divided by 8m. Okay, so you can see that bound state exists for V naught greater than h bar square pi square by 8m a square. Okay, this is the sufficiency. This is the sufficient condition. Sufficient condition. Okay, your V naught should be some threshold. This is the threshold value. Only if V naught is bigger than that, then there will be a bound state. So what I'm trying to say at this point is that suppose if you have a potential well like this, let's say you have a V naught like this. V naught is small here. Okay, so since for this if V naught is less than h bar square pi square by 8ma square. Okay, so this is your A width. Then even if E is less than V naught, okay, the particle is not bound. Okay, so this is necessary, but it's not sufficient, because if V naught is less than that, then even if this is so, then it is not bound state. But you should have this condition. V naught should be above this, and then E should be less than V naught, then there exists a bound state. So this is what we have. We have the now. If you want to find out what are the energy levels, you have to actually take a graph paper and then try to plot these two curves and then carefully locate these intersection points for a given value of V naught. You have to locate these things. Okay, so that is the exercise that one has to do. But I would like to look at a limit. Okay, so let's look at a limit. Suppose if you take if you take take the limit V naught tending to infinity. Okay, physically we know that if V naught is tending to infinity, this becomes particle in a box. Correct? You have one side anyway infinity. Okay, so it is a particle in a box. But this implies the radius of the circle in eta xi plane is infinity. What does that mean? That means your in this graph you have some infinity. Okay, so that means it has some infinity. That means all of them will be intersecting this at pi and 2 pi and so on. What does that mean? You are okay, so that means your xi is equal to n times pi. But what is xi? Xi is Ka. K is equal to m pi. This is exactly the condition of particle in a box. Okay. So this is a feature that you can see that this goes to particle in a box conditions in the limit V naught tending to infinity. Okay, so now let us look at a situation where we have square well potential. Okay, so let's look at this case. Now let's look at square well potential.
Sir, one small doubt again.
Yeah.
Sir, I could sense a circle, even if the circle is less than, circle's radius is less than pi by 2, I could sense a circle intersecting the chord graph below the y-axis.
Okay. So okay. So you can see that just note this one here, that your what is your xi? Xi is equal to k times a, correct? That is equal to square root of twice m e by h bar square into a, correct? And eta is equal to alpha times, did I use alpha? Yes, alpha. So that's equal to square root of twice m into v naught minus e divided by h bar square into a. Okay. So in this particular case, by definition, your xi and eta are greater than 0. Okay. They are greater than 0. Even though I have drawn this like this, but physically only the first quadrant is relevant for us. So we have to only consider the intersection that happen in the xi greater than 0 and eta greater than 0. Okay. So only this first quadrant is physically relevant.
Oh, okay, sir. Now I got it. Because it intersects in the fourth quadrant also, but
Yeah,
psi
yeah.
and eta are greater than 0.
Yeah, but this is what is physically relevant. Now, if you look at the square well potential, supposing if I have both sides, it is let's say this is 0. Okay, or you could have simply taken this as v naught here and v naught here. So maybe I take this also as v naught and this also as. Okay, and that means what is the difference between this and the previous problem? One side there was an infinity at least there. Now both sides it is finite. So this is like square well potential, correct? So now suppose if you consider e less than v naught. Consider e less than v naught. So this is essentially the bound state problem. Okay. So you can see that okay, let us try to do this calculation. Let's call this as 0 and this as a. Okay. So what will be the wave function in the psi1 case? Psi1 of x. So let's say this is region 1, this is region 2, and this is region 3. Okay, so that is equal to e to the power alpha x, because x is less than 0 now in the region 1. Okay, and psi2 of x is, okay, so maybe I should write it as A here, and B cos kx plus C sin kx, and psi 3 of x is equal to d e to the minus alpha x. Okay, so alpha and k are same as in the previous case. So alpha square is equal to twice m into v naught minus e divided by h bar square. K square is equal to twice m e by h bar square. So now you can see that at this boundary, okay, so at x equal to 0, at this boundary, we will have A is equal to B. We have A is equal to B. And the derivative, this is psi 1 of 0 is equal to psi 2 of 0. So if I use this, then I have this condition. Now psi 1 prime at 0 is equal to psi 2 prime at 0. What does that give you? Alpha times A is equal to K. So this is minus bk sin k. So ck is equal to c times. So you can see that my c is equal to alpha by k and b is equal to b. Correct. So now I can write down my I1 of x as a into e to the alpha x, and because of these two boundary conditions, my psi 2 of x is equal to a into cos kx plus, okay, cos kx plus alpha by k into sin k. Okay. Now let's look at the boundary at x equal to a. At x equal to a, so you have psi 2 of a is equal to psi 3 of a. That gives you a times cos ka plus alpha by k into sin ka is equal to b into e to the minus alpha. Psi 2 prime of a is equal to psi 3 prime of a. So which is equal to a minus k sin ka plus alpha cos ka, because a k will come out, that k will cancel with this k, is equal to minus d alpha e to the minus alpha. Okay. So now you can see that So now I can write. So this I can write it as so if I divide this one, that is minus k sine ka plus alpha cos ka divided by cos ka plus alpha by k sine ka, this k will get cancelled, is equal to minus alpha. So this equation is somewhat like our previous equation. So this is the equation that we have to use to solve the allowed values of k. Now we should get suppose if I write this, suppose if I pull out a cos ka from the numerator, so if I pull out cos ka, then I have minus k tan ka plus 1 plus alpha, and from the denominator also I pull out a cos ka, then 1 plus alpha by k tan ka is equal to minus alpha. So this cos k will cancel. So I have, let's write this as k by alpha. So if I pull out an alpha from here, I have 1 minus k by alpha tan ka, and that alpha will cancel with this alpha by 1 plus alpha by k tan ka is equal to minus 1. Or you can write this as 1 minus k by alpha tan ka is equal to minus 1 minus alpha by k tan k. So when I take this, it will become 2. If I take it on the other side, I have tan ka into k by alpha minus alpha by k is equal to. So that is equal to tan ka into you have k square minus alpha square by alpha k is equal to r tan ka is equal to 2 alpha k divided by k square minus alpha. Okay, so this is I do not know this Usually this problem will get nicely divided if we use what is called a reflection symmetry about the origin. But I tried to do it with 0 to A just because we have done previous problem like that. So, but anyway, let me just tell you the story. The story is that if you if you try to plot this, left hand side and right hand side, you will see that the tan function will pass through the origin. Suppose this is your pi by 2, and your tan function will have a graph like this. Now, if you look at the first quadrant, the right hand side will have some kind of a graph like this. Now, whatever is your V naught, okay, there exists always one bound state. Because suppose the V naught is very small, then this curve may be like this. Okay? So, because of this condition, okay, for every V naught, there exists at least one bound state. One bound state. That means there is no threshold, V naught necessary for existence of bound state. Okay. Now, why do you think this is so? Why do you think this is so? In the previous case, they required some threshold V naught, but now there is no threshold V naught that is required. At least one bound state you can get.
So as that graph goes to origin, so if we have any energy like any V naught, okay, we can always have a like the circle can be so small, but we can have an intersection.
What?
So the two cars intersection, if in at because it is going through 0, the tan x is going through 0.
Yeah,
We will always have some intersection.
that is correct. But what is that is what we have found mathematically. But what is happening physically? Why there is a threshold V naught required for the one-sided well, and why there is no threshold V naught required for both-sided well? Is there any physical way to understand this?
Sir?
Yeah.
Sir, if we plot the wavelength in both cases, finite and semi-infinite, from that we can understand. Means in case of finite square well, the wavelength in principle can be infinite. So, there is no means the energy can be 0 this case, right? If we say from de Broglie wavelength, if we write the energy H, so there exists no threshold is not required this case. But in other case, sir, if you see, is it correct, sir?
Yeah, I think you are making the point. So essentially, what you are saying is that suppose if you have a wavelength, then it can actually go inside these two regions like this. Okay. So now this can be even bigger. You can actually have something like this. So this is how the bound state looks, because this is bound here, and then it exponentially decays on both sides. So whatever is the smallest V0, you can always find a wave function which can penetrate into both the regions. But on the other hand, if one side is infinity, you cannot penetrate this side. It has to go to 0 here. Okay, so only one side you can penetrate. Okay, so because of that, you will not be able to have a bound state, because if it can penetrate both sides, you can have remember, your wavelength is what? In this region you have k, right? So your k is equal to twice m e by h bar square, and your wavelength is 2 pi by k, correct? So that is equal to 2 pi h bar square by 2 me. So if your wavelength, if energy goes to 0, then the wavelength goes to infinity. Okay, so if the wavelength goes to infinity, that means you are in this particular case, it can go to infinity because it can penetrate into both sides. Whereas here it cannot penetrate to both sides. So your energy going to 0 is not a possible bound state in this case. So that is the reason why for a square well potential it exists. But you can notice that I mean, if you have done these problems in 3 dimension, if you take a 3-dimensional square well potential, that means let's say you have some region in which there is a 0 potential or minus potential, okay, radial square well potential, then such a thing is not true, because there you have a centrifugal potential always. Okay, that comes because of the finite angular momentum, and because of that you have repulsion at very close r equal to 0, r is very close to 0. So it will be once again like this one-sided thing. So you require a threshold for existence of a bound state. So one-dimensional square well potential is the only case where there exists one bound state for every possible V0. So that is the physics of this problem. So I think we have looked at some set of problems today, which are essentially again kind of free particle potential well problems, but they have they are definitely the basic problems that we have in front of me. And I'm sure for some of you this will be a kind of repetition, because these are problems which are done in every quantum mechanics course. But nevertheless, we can understand some techniques and some bookkeeping and some physics. So I will stop here, and if you have questions, you can ask.
Sir?